Hello and welcome to another video, this time where we work through a problem by hand on the topic of regression. Now, this is very closely connected to correlation, as we'll see later, and you'll see the details of the early work we have to do will look very, very similar as well. But I separate these to a different topic just so we can section it in our minds. So we have already done a lecture on this topic. Now we are looking at a specific problem, sort of a representative problem, and see all the things we should be able to do by hand to understand the inner workings behind this question or this type of question. So the book, as always, that we are going to look at, Statistics for Psychology, we're going to go to page 535, looking at problem 15. Now, if you've done this in order, this should look quite familiar in that this uses the same sample as for the one we did, number 12, in the previous topic on correlation. So we're given 4 individuals. We tested dexterity and anxiety on some score, and we want to interpret these results. Now, we don't know which one causes which, but there we saw that the evidence suggests there is a connection between these. There is a correlation. We want to establish a rule, a linear prediction rule, to predict one score from the other. In this case, predict anxiety from dexterity. So given the dexterity score, what is the predicted anxiety score that would be associated with that? Then we'll draw the regression line, or at least see the data points again. By hand, of course, there's some imprecision when we have to draw the line by hand, but still gives us a visual on what's happening, which is helpful. We'll use the linear prediction rule to make some predictions, and then we'll also determine the standardized regression coefficient and see its connection to the correlation coefficient. And of course, even though we don't write part G, as we talk about it, we are essentially answering part G. We're not going to do H because we're just introducing the topic at this stage. All right, so let's start by writing down the number, maybe. That'd be good. Listening to people. Person 1, 2, 3, and 4. And I'm gonna need some columns here. We're going to use X as the dexterity variable. Dexterity. Why? Because, how come? Because they want me to ultimately make a prediction rule that gives me anxiety when the input is a dexterity score. So I see X as the input and Y as the output. So X will be associated with dexterity, Y with anxiety. So I'll have my X scores here. I'll just copy them over. 1, 1, 2, and 4. We're going to do some stuff. We're going to calculate the deviation from the mean. We're going to look at the squared deviation from the mean. So this time I want to plan my columns here. Then we will have our Y variable, which will correspond to the anxiety scores. Copy those down as 10, 8, 4, and -2. We'll have some deviations from the mean. square deviations, sure. And ultimately, our goal will be to calculate in our prediction rule. Let's write down the prediction rule here. Prediction rule that we're trying to establish is y with a little hat for predicted y equals some constant a plus some constant b times the dexterity score you want to use as input. Now, these are not all given in a formula sheet in this book, unfortunately. We have this general prediction rule formula, but not the A and the B. So I'll add those here so you can make your own extra formula sheet if you need to. The B is going to be calculated using these deviations from the means in both cases. And then we're going to pairwise multiply them together, add them up, and divide by the sum of the squares in the x variable. So here what we're going to need is to multiply the deviation scores, so to speak. That'll be needed in our calculation. We're going to add them up here, divide by the sum of the squares, which will be this column over here, right? For the x variable. And that's going to give us our b. Then after we get b, we can calculate the a by taking the mean on the y variable minus that b that we calculated times the mean in the x variable. Now, at this stage, in case you're wondering, like, where on earth these things come from, the derivation of these formulas are much more complicated than using them and making progress in seeing these practical problems and how these prediction rules have relevance. Coming up with these and deriving why the formulas look like this, well, that is much more complicated. It's not really in the scope of this introduction series of videos, unfortunately. So our goal here is to just use the formulas to find the A and the B, and then we'll use this linear prediction rule. If you think back in high school, this has the form y equals mx plus b, but of course the m and the b have different roles here. The slope here now is called b, and the intercept is now called a. Regardless, in order for us to get here, we need to fill in these top numbers and do some calculations. Similar calculations to when we calculated the correlation coefficient, not exactly the same. So we have to find the mean. Now I think they're nice enough here to give us the mean 2 and 5, just to save us some effort. But of course we can calculate that ourselves as well. Add up all the numbers here, divide by 4, and we get 2. But they're just saving some time. That's not where that column goes. Over here. Mean y score, 5. You add them all up, you get 18, 22, 20 divided by 4 is 5, yes. Okay. So nothing special there. Now we don't need to calculate the variance completely in the standard deviation like we did in the correlation coefficient case. We sort of go halfway with the sum of the squares. And that's all we really need. So we need to calculate the deviations and then square them. Deviation from the x values to the x scores rather to the mean. 1 minus 2 will be negative 1. This will be a negative 1. 2 minus 2, this will be a 0. 4 minus 2 will be a 2. Now we square them, 1, 1, 0, 4. And then the sum of the squares, obviously here, is a 6. And we need that guy at the bottom here in our B formula. So that's it temporarily for the X variable. Now we do the same thing for the Y variable. Now these numbers could be much more complicated, and then you have more calculator work to do. We keep it simple to focus on the process instead of running to the calculator every single time. So we have a nice mean to work with. 10 minus 5 is a nice 5. 3, 4 minus 5, negative 2 minus 5. Just for convenience as a first problem to work through. Then we square them, 25, 9, 1, and 49. We are going to need this guy later, so I might as well do the sum of the squares of y now. We add these up, 25 plus 9, that's 34, 35, 84. So we don't need the sum of the squares for y in these formulas. We do need it for the standardized regression coefficient later. Now we have to multiply, not the square deviations, just the deviation scores. So negative 1 times 5, negative 1 times 3, 0 times negative 1, and 2 times negative 7. We add those together for a sum of negative 22. So that is this numerator in the B variable, constant. Negative 22. Sum of the squares here is 6. And we can go to the calculator for that to do something. It's lonely, it wants to do something. Negative 22 divided by 6. And we get a negative 3.67, we'll say. We then use that in here to calculate the A constant. Mean of y is 5 minus this negative 3.67 times mean of x is 2. Let's do that. Why not give the calculator something to do? I'll just say 5 plus 3.67 times 2, and we get our 12.34. So perhaps I'll rewrite the prediction rule. Prediction rule, we now know y hat 12.34 minus 3.67 times x. Okay, there it is. Now, I'm not going to do all of these predictions that they want. They want us to predict the anxiety. Actually, yes, they want us to predict the anxiety for people with dexterity scores 1, 2, 3. I'll just do 1, right? We plug it into this prediction rule, plug x in, get a predicted y value, nothing to it. However, I did forget to draw the data points and the line. So let's quickly do that. We'll squeeze it in maybe on the side here. Now this is exactly the same as the previous problem video, which would be topic 10, B1, where we just went 2, 4, 6, 8, and 10, and a negative 2, and then a 1, 2, 3, 4. First one was 110. So up here, then we had 1, 8. Oopsie. Then we had a 2, 4, 2, 4, and a 4, negative 2. And in the previous problem on correlation, we looked at this and we said, could be negative correlation there. We're not sure until we actually test it for significance, but still. So now this is just by hand, so it's going to be a little rough drawing this straight line, which has decimals in it. But remember your y equals mx plus b. There are multiple ways to go about this. The simplest, arguably, that I could suggest is this constant here, 12.34, also called the intercept, will sit, I'm a little out of space here, so let me just move this up a little bit. Move it up a little bit. And let's put 12 over there, 12.34. I'm going to use a color here. Let's use purple. It's not a data point. It's just a point that helps me draw the line. In order for me to draw a straight line, in the simplest case, I need 2 points that sit on that line. Connecting those 2 points will specify the line uniquely. So there are 2 simple points where the line crosses the y-axis and where the line crosses the x-axis. Where the line crosses the y-axis, that'll correspond to an x value plugged in of 0. Now 0 sits over here, right? When I plug in a 0 for x, the purple value of 12.34 is exactly what I get. Now I can't be super precise here, but that is what that purple dot is all about. The other way around is when the y predicted value is 0, what would the x value be that corresponds to that? So we call this top one the y-intercept, which is convenient because it's right in the formula. We call this a slope-intercept form of a linear, let's say, prediction rule. The other one, unfortunately, is not that simple, but we plug in. I'm going to go a different color here. Let's change the color to maybe a pinky. Pinky. There we go. So for that one, we're going to set the output at 0. And then we solve for x. Again, not the only way, but to do it by hand, finding 2 points is one of the simpler ways. So I get 12. I'm just going to flip everything around because it feels better for me. And put the 0 on the other side. 12.34 minus 3.67 times x equal to 0. How do I solve for x? Well, I could subtract 12.34 on both sides. Then I get negative 12.34 on the other side, and then divide both sides by this coefficient. And then we get x as, and again, this is just a point on that line. I only do it in order to draw the line. There is no other reason at this stage. So I get 3.36. So 3.36 roughly over here. 3.36 called the x-intercept. And this is how I could find it. So then let's pick another color. I like color. For the predictor line, I get by just connecting those two. Now I'll extend it in other direction, like so. It goes on forever or until the scale stops. And you see how it is trying to find its way, the best possible fit through these points while being a straight line. It's not going to sit perfectly on them, but it's minimizing all these little errors between the line and the data points themselves. All right, so handy to visualize. It's good. Must be able to do that. And this is one way to do it, by hand. So there's a lot of value that I get by doing these problems by hand first, before running to software where I feel detached. I don't really know what it's doing. I just sort of believe it, I guess. Don't really know what it's doing. I'm more connected to it when I do it by hand, at least in the beginning. Okay, so we have our rule. We visualized it. Let's make a prediction here in part C for dexterity of 1. The predicted anxiety is, well, we plug it in, 12.34 minus 3.67 times 1, that score of 1, and we get, I'll just do it so we can see, 12.34 minus 3.67 times 1 in this case, and we get 8.67. Now maybe the score in anxiety can't have decimals like that, but it still gives us an indication. Between 8 and 9, we perhaps would have to say. All right. So this was B, where we draw it, C, where we make a prediction, and I'm going to leave it to you to make predictions for dexterity 2 and 3. Okay. Next, we want to determine the standardized regression coefficient. Now, we've discussed in the previous video what that does. It's not really something to get into here, really. For the simple case where the predictor variable, where there's only one predictor variable, one input variable x, this is the same as the correlation coefficient. And previously, remember, we got the correlation coefficient in the video 10 or topic 10 as negative 0.98. Negative 0.98. But in general, when I have multiple predictor variables, these two are not necessarily the same for more complicated situations. So they do name it differently. Unfortunately, this is also not in the formula sheet. Don't ask me why. I didn't write the book as good as the book is. It is unfortunately not there. So I'll give you the formula. It is the B coefficient in my prediction rule times the square root of the sum of the squares of x over the square root sum of the squares of the y variable. So let's see if we can calculate that and verify that it is in fact the same as the correlation coefficient, which we'll see an interpretation that's very commonly used in a second. So let me calculate the B. What's the B? It's negative 3.67 times square root of sum of the squares of x. It's up here was 6, and the other one was 84. All right, so square root of 6 divided by square root of 84. And we get our negative 0.98. And these will be the same in the case where I have one predictor variable x, which is certainly the only case I can handle by hand. Then lastly, I want to do two things. I want to interpret the slope. I'm just trying to think of things not necessarily in this question explicitly asked, but things I might need to be able to do. Interpret the slope in my prediction rule. The slope is b, and in this case it's negative 3.67. What I like to do is I like to write it negative 3.67 over 1. And then I have to think back high school. This slope is the change in the y variable over the change in the x variable. Predicted, but still. Okay. That is the slope of a straight line. So that means that if I change if there is a change in the x variable, now I always start bottom up in my interpretation sentence. And I like to always do the same thing because it builds confidence. Bottom first. If the x variable changes, in this case an increase of 1, then there will be a decrease in the y variable, or a predicted decrease of 3.67. So see, this is a plus and a minus indicating increase and decrease. So we're going to say that. If, now x is dexterity, if the dexterity score increases by 1, then we predict a decrease of 3.67 in anxiety. Whatever scale is used, of course. It's very important, I feel, to be able to interpret these numbers that I see in the prediction rule. We've already interpreted, maybe you didn't realize, we've already interpreted the other number, the 12.34. That is the intercept where the x score or value is 0. What is the predicted y? So a 0 on the dexterity scale will give a predicted anxiety score of 12.34. Not as useful to interpret as the slope, because very often the 0 is a very extreme, unrealistic situation. Whereas the slope gives me a general trend of if the variable changes, how does the prediction change? So that's very valuable. Lastly, we have space for one more. We want to calculate R squared, the square of the correlation coefficient. In this case, I'll do it. We calculate negative, I'll do it in brackets, negative 0.98 squared, like so, and I get 0.96. I then convert that to a percentage, and this is always going to range between 0 and 1. The R squared in percentage form tells me how much of the variation in the y variable, the output variable, the predicted variable, is accounted for by this predictor variable x. So in this case, I have to remember what they mean. There is, of course, variation in the anxiety score. That's Y, anxiety, right? And oops, I have to write that down here. Anxiety. There is changes from one person to the next in anxiety scores. How much of that change is accounted for by dexterity? There are potentially other factors that affect, directly or indirectly, that affect anxiety. Dexterity, it seems, is one of them. How much of the variation in anxiety is attributed to dexterity? The R-squared gives me that. So in this case, it's a very high percentage. And we can say 96% of the variation in anxiety scores is accounted for by dexterity. So because dexterity scores change, anxiety scores will change. But dexterity is a very strong, don't want to use the word strong, it's a very big predictor of this anxiety score. It's a major player, not a direct, it's not about causation. It's about making a prediction that with a high R-squared, with a high squared correlation coefficient, a large portion of the changing Y variable comes from that X variable that I'm considering. There are, of course, other factors, but this 96% tells me that they aren't big players in making a prediction of how anxiety will change. The major players, so to speak, in this case, to make a prediction for the change in anxiety will come from dexterity. If I have a very small R-squared, then yes, that variable is used in making a prediction. It does affect change in the Y variable, but not a lot is attributed to that variable. There are some other variables that have bigger effects directly or indirectly. So I wanted to end with these: interpret the slope of my prediction, my linear prediction rule, R-squared, and what that tells me about the connection between these variables. And of course, that's very closely linked to correlation. It is the correlation coefficient. Hopefully that gives you a fairly good base to build on, seeing how these things are calculated by hand, some more interpretation things behind what we're really trying to establish here, a connection between these variables. And it's important to be able to interpret that in words. All right, that is the end of this video. I will see you next time. Until then.